Hello class, welcome to our session. Today we're looking at a number theory problem from the SAT. This question is all about divisibility. It gives us a number, x, and tells us how it behaves when divided by 3, 4, and 11. Our job is to figure out what else we can say about x based on this information. Let's dive in. The first thing we need to do is translate the problem's language into a simple mathematical concept. As you see on the screen, the key phrase is the remainder. Dot is 0. Whenever you see this, you should immediately think is a multiple of. So the problem is telling us that x is a multiple of 3, a multiple of 4, and a multiple of 11. So let's officially lay out what we know. Step 1 is to fully understand the conditions. As we've just discussed, this means x has to be divisible by 3, 4, and 11 with no remainder. You can see it listed clearly. X is a multiple of 3, x is a multiple of 4, and x is a multiple of 11. It's not one or the other. It has to be all three simultaneously. Now for step 2. Since x has to be a multiple of all these numbers, we need to find the smallest number that satisfies this condition. This brings us to a very important concept, the least common multiple, or LCM. As the text states, if a number is a multiple of several other numbers, it must also be a multiple of their LCM. So, our task is to find the LCM of 3, 4, and 11. To calculate the LCM, we first look at the numbers 3, 4, and 11. Do they share any common factors other than 1? No, they don't. This means they are relatively prime. When numbers are relatively prime, finding their LCM is very simple. You just multiply them all together. As you can see in the equation, we calculate 3 times 4, which gives us 12. Then we multiply that by 11. So 12 times 11 equals 132. This means the smallest positive number that is a multiple of 3, 4, and 11 is 132. This is the most important conclusion we've made so far. We now know that any number x that fits the problem's description must be a multiple of 132. It could be 132 itself, or 264, which is 132 times 2, or 396, which is 132 times 3, and so on. We can express this with the formula x equals 132k, where k is any positive whole number. All right, let's move to step 3. The question asks which of the options must x be a multiple of. We've just established that x must be a multiple of 132. So we can rephrase the question like this. Which of the answer choices is a factor of 132? If a number is a factor of 132, then any multiple of 132 will also be a multiple of that number. So now we'll go through the options one by one. Let's start with option A, the number 6. We ask ourselves, is 132 divisible by 6? A quick calculation shows that 132 divided by 6 is 22. Since we get a whole number, the answer is yes. So 6 is a factor of 132. This looks like our answer, but let's be thorough and check the others. Next is option B, the number 8. Is 132 divisible by 8? When we divide 132 by 8, we get 16.5. Since this is not a whole number, 8 is not a factor of 132. Continuing our check, we move to option C, the number 16. Is 132 divisible by 16? The result is 8. 25, which is a decimal. So 16 is not a factor. Finally, we have option D, the number 47. we can see pretty quickly that 47, which is a prime number, does not go into 132 evenly. So option D is also incorrect. This brings us to our conclusion in step 4. After checking all the options, we found that only 6 is a factor of 132. Therefore, any number x that is a multiple of 132 must also be a multiple of 6. The algebraic proof on the screen makes this very clear. If we know x equals 132k, we can rewrite 132 as 6 times 22. So x equals 6 times 22 times k. This form shows that 6 is always a factor of x, no matter what k is. So the final result is that the correct option is A, which is 6. By understanding the meaning of remainder of 0 inches using the least common multiple, and then systematically testing the options, we arrived at the correct answer. This is a classic SAT problem that combines vocabulary with number properties. Well done, and I'll see you for the next problem.